Hvis vi får lov å headbande til Marcos, så skal vi gjøre raskere.
Ja, da tar det 6 uker. Eller det kommer,
vi må jo bytte på da.
Så det kommer til å ta...
Welcome. Thanks for joining today. It looks a bit inquisitive, doesn't it, from your perspective? Anyway, it wasn't me, sorry. So welcome 8 people. Today we are continuing our, I guess, exploration in graphics a bit. So before we go deeper into lighting, because we have this prototypical disconnect between labs and lectures again, we probably need to do something else in between, but it probably makes sense anyway, because something that's particularly relevant for you guys, I suspect, as potential developers of a game engine or the like, but perhaps not necessarily as modelers. It would be quite interesting to actually see how you actually, what formats exist that you can use to read, 3D models that you can use in your application and the like, right? So, does anyone have experience with this one? Yes?
STL, for example, it's just a bunch of vertices and then data describing which vertices are connected.
Yep, cool. So yes, that means I picked the wrong example because I didn't pick that one. So you can fill in the gaps if you find some feature set in the formats that I'm describing and that you feel STL does better. I think it's a bit of an older format, isn't it?
Yeah, it's a dinosaur.
Yes, okay. Well, that puts it...
Still in use though.
Yeah, of course. No, that's right. So the point is there's an abundance of them, but that's probably worthwhile looking into a few of them, specifically the ones you're going to be using, and then perhaps see how far we get. Perhaps look into having a mini implementation of an object loader for one of the formats that you most likely encounter the most. So up to now we look into geometric shapes, transforming, skinning as a simple way of, as a shortcut to have color on some objects, on some geometric shapes, so it looks okay. And then basic lighting, which is a bit more an advanced way of modifying the color information, right? That is attached with a particular, pixel or particular coordinate in your object you're modeling. But the shapes we have been dealing with were quite primitive so far, right? So in either you were given some sprite sheet, you could use them. The animation was probably the most challenging bit there, if you like, but other than that, we actually didn't push it too far. And the idea is that we probably shouldn't either. So, I mean, it's a graphics programming course and not so much graphics modeling course because I have no clue how that works. So, but you obviously know the tools you use that, which would be classically, typically Blender, right? So, which you guys may have come across. Blender? No? Yes? Yeah? Somewhat, right? So we're not going deep into that one, but we're going to deal with the output they actually produce. And particularly if you have larger objects, managing by hand is quite tedious. And because you can't keep track of the geometries and their relationships and so on, that's not necessarily too straightforward. And if, in addition to the vertices and the shapes or surfaces that they generate, if you have things like texture coordinates on top of that one, you need to model them and keep track of them, it becomes really tedious to, I think, retain that relationship. And the third thing is basically that, whoever models, 3D objects and the like, is not necessarily a game designer, and that may not even the engine developer. So there's a natural disconnect between the, or oftentimes there's a disconnect between all 3 of those, right? They want to speak the same language-ish in order to work with this on this. But still, they're not necessarily using or producing the same format, but possibly consuming it. So, and the third aspect, there is a considerable market anyway in the meantime just for modeling, right? So, if you provide 3D models that you can use in your game or in your application, or for perhaps more realistic or real-world purposes like architecture or the like. So, then there is a considerable market there in the meantime. And so yeah, probably can just show those 2 sites that I think are quite representative in terms of doing that. if you guys know another good site that is worthwhile mentioning here, but obviously from the economic point of view, there's quite a bit of opportunity to actually model and sell eventually for a given price or not, and you have all ranges of objects and complexity and also prices. So it ranges from $5 to $1,000 and more, obviously. So, but it's a dedicated market in itself. So if anyone wants to go into that area, there's obviously a space there to do that. Looking at the more academic perspective, where it's more about demoing models that are relevant or are a good benchmark of quality. And this side is quite worthwhile mentioning, Causal Effects, if you haven't come across that one. But you also notice that there's a bit more of information available. They have a quite a wide range of different shapes, and some of them may be familiar to you already, right? So, for example, this box we had seen before in the last session, right? So it's referred to as the Cornell box, which is used to assess quality in terms of for ray tracing, reflection, and the caustic effects and so on. So, and another one is the Stanford Bunny, which is known for its complexity of the surface shapes. So it's about smoothing in particular. How do we accurately represent the fur so it doesn't feel like a flat shading approach, right, where we have those rugged surfaces. So, yep.
It's also popular to 3D print due to the way its ears are shaped, so it's challenging to have the ears look nice. Yes.
And keeping them attached and not dropping off because the glue is settling. Yeah, that's right. Good point. Yeah, so that's quite. And the obvious one, I think they have it here as well. No, not the cube. The Chinese dragon, right? That's one of them as well. Also, complexity is the thing. But obviously, where is it? The coffee pot. There must be somewhere. So was there already? The Utah coffee pot is here as well. I think I spotted it. So there you go. Yeah. That's one variant of it. It can't be missed there. So the point is, but here's quite a bit of, quite a number of interesting models. And the interesting thing is actually if you look at the complexity. So we have here, we're dealing with 15,000 triangles. But I think the most complex I saw was here on that page anyway. I think this one, 6 million triangles. So, and this is 12 million vertices, which kind of makes sense. And yeah, the room hole setting, which is kind of a Minecraft map or derived from Minecraft map, and it's a kind of a semi-new reference for object loading. So because question how many objects or how many vertices can your loader deal with in a considerable amount of time or a small amount of time. So has found some attention there as well. But so there's quite a bit of data available, but the complexity is actually fairly high. So if you look, for example, at, I think I downloaded this thing. At the file size is around, what did I mention before? 48 megabytes. I'm not sure if I downloaded that one. So anyway, but we'll see some examples for that later. Anyway, so there's a large, considerable amount of models in the meantime that are available, and there's a demo of some of them, so some pointers. Anyway, if you want to browse and explore, that's worthwhile. But the question is, so what are the formats that you should consume or produce in, right? Because you want to be generic, assuming you're writing your own, engine, so rendering engine in OpenGL, and you want to use pretty much arbitrary models. It's probably worthwhile to have a rough understanding about different models, the formats that exist now available for that. And generally, the usual differentiation is between the proprietary stuff and the open stuff. And then it kind of usually goes in line with binary versus human readable, because that obviously obscures the internal structure of a given format. And second one is the transfer. We find that some formats are more widely read and accepted, but they may not be the most featureful, so it's more like a compatibility approach of sharing models, and you later need to refine it. Whether they support textures, animations, or even interaction with the user, which can be quite useful. So, do you guys know any models apart from STL?
OBJ.
Yeah, there you go.
But contains textures, I think, and mapping to those textures.
Yeah.
You can just throw them into any environment and have them rendered correctly.
Yes, that's right. So that's one of the ideas. Any other? No, cool. So there's a list of them you've kind of found slash collated here that you find in terms of possible formats. So more classical ones like from 3D Studio Max, which is kind of a industry standard in the meantime in terms of formats, but it's actually a binary format, so it's not like super transparent in terms of its functionality and so on. But then you have obviously internal Blender format. It's similar to the 3D Studio Max. It obviously has more generic components that are read by any other by any tool that's able to import the corresponding format, but obviously also some sort of Blender-specific extensions that are involved in it. So, but it's not too generic in terms of being read. I'm not sure if there's any other framework that actually deals with this properly. Few exceptions for model loading in C++. From an industrial point of view, AutoCAD, mostly because of its accurate units. So those, I'm not sure about Blender, but this one, for example, doesn't have an absolute, it doesn't have a, you can't encode units, right? So you can't actually indicate something in centimeters or in meters or millimeters or whatever else, whereas in the industrial formats that are focused on computer-aided design, it's pretty much a standard, right? Because you want to be able to reproduce, do potentially CNC rendering, the old version of 3D printing, I guess, or things like that. So you need to have a format that supports that. And there's a wide range of other formats. You may have, I'm not sure where's Stanford one. It's not on here, but the Quake model files that were quite in a given. Are they still used? Do you guys? So they were usually used in the Quake engine to model the environment. Were quite interesting for modders there. And yeah, various. I mean, every tool that's on the planet, I think, came up with its own format. No, not the tool, rather the developers. But nevertheless, so and obviously more interesting ones like OBJ, which is also actually an industry-based format, but it's open, and that makes the situation quite different because you can easily inspect it and has had massive uptake over the years, and still has. We'll get into that a bit more in a second because it's worthwhile to explore that a bit. What else? Oh yeah, from BPROG. So it's a ray tracer that has its own format. That's quite well known. Is there anything else? Yes, right. We have virtual reality modeling language. Even though it sounds contemporary, it's actually deprecated. So it's a very old language, human readable, standardized. I think it's standardized by the Web3D consortium to represent models, but particularly with focus on virtual reality in web content. That was the idea, but it didn't really take up, or wasn't really taken up ultimately, and has been kind of substituted by X3D, which is kind of a modern variant of it, completely written or specified in XML, and extends the features with focus on interaction. So it's this particular strength. So we'll have a look at this as well. So, but first of all, I think the most important format that we need to deal with is the OBJ format. So, as you mentioned, so it's kind of powerful and has a its particular striking features are basically there's interoperability and human readability. So it was originally developed in the 80s by what was referred to wavefront technologies, and the tool that used it or introduced it was the advanced visualizer. So which was actually not one tool, it was basically a set of tools that needed to exchange the data they were modeling with. So for example, there was the modeling tool, there was the painting tool that was focusing on colors, kinemation, and format checking tools and so on. So there was quite a bit of independent tools that were kind of combined into some suite. And the challenge there was they actually needed to have a common shared format, so they actually could do interchange within the own tool suite. But because of that one, the specification had been so reasonably well known and simply widely adopted. So it's just the first comer advantage there. Quite straightforward, ASCII format. We'll get into that format details a bit more in a second. But you can also comment in addition to actually doing the specification. Why am I mentioning this? Because this has been subject to some proprietary extensions that people actually encode meta information into the comments that they use in their own model reader or model loader, right? So you can actually encode more information there, but retain compatibility to the core model. But of course, you're also free to extend the specification. Similar to the earlier one that I mentioned, 3DS, is that it doesn't have an absolute unit specification, so it's a bit nasty. It actually, has only relative sizes, measures metrics, but again, you can encode them if you want to. Wide support, broad feature set. Yeah, one thing that I realized when playing around with this, that there is quite a bit of models that are not necessarily compliant with the core specification, but have experienced some extensions that are specific to a modeling environment. And if those extensions are not supported, or the tool that you're using doesn't consider the fact that people actually muck around with this format, then it may just break when you open a model file. So that's not ideal, but that's the way. That's basically the way it goes with this format. But right. So to look at, perhaps to give a bit more of an intuition before we dive into some of the syntax elements, because that's the one we'll be mostly dealing with. Let me bring up that format. So this, for example, is a cube representation. Hang on, if I'm clever enough, I should have. Yeah, so there's a bit an issue with the textures availability, but I tried to run Blender on my machine and I can't do anything else. So I decided to opt for a lightweight tool that still allows me to do something but doesn't look beautiful, because beautiful is secondary right now. But the idea is there that you basically can, have a cube representation in that form. Come on. Ah, there you go. Oh, that's super laggy. All right. I'm not sure if there's any remnants of a stream left, but probably not for long. So, yeah. So, okay, that's the cube, but you get the gist here. But what I actually wanted to show you, so I minimize this thing in case to prevent my machine from blowing up eventually. You may not be able to read it. So let's try to increase it. Thank you. It's my favorite tool of choice, but it doesn't seem to have a zoom feature, which is not helpful in that context. So let's use something more conventional. All right, cool. So yeah, barely readable. But anyway, I'll go through with some of the intuitions, so then we'll look at the specification. It all makes sense anyway. But what that basically does, it sequentially defines components of your model, right? So, and it usually syntax as follows: keyword and then the actual metrics associated with this, right? So, symbol and so on. And obviously on top there are some comments which suggest that this model has been written in Blender, so no surprises there. And the second line, it says, well, there's actually, that's where it becomes interesting, there's actually a material representation attached to that object. So what the OBJ format does by default is separating the geometric representation from appearance, right? So for material data, and that's quite interesting in terms of firstly considering that one, but also maintaining that relationship. And then we see here V, VT, VN, and F. Those are the most important features anyway. So, and V basically specifies what? Any guesses?
Vector point.
That's right. Yeah. Yes, that's right. So we basically have a vertex representation. Can be 3 or 4 dimensional. And I think we get the gist: X, Y, Z, X, Y, Z, and so on. It does that, basically sequentially. The order is not relevant. So it could be mixed up. It could also intermingle any of those different statements. So the blocks don't need to be coherent, at least for that kind of format here. We get into cases where it's more relevant. The second one is VT. Any guesses? So it's a 3D model. In which case did we have a 2D vector to represent something in 3D models?
I don't understand the values.
Don't worry about.
But
Understanding is very secondary right now.
Is that like which vertices are connected? So from any vertices, which other vertices connected?
Yeah, nearly. VT stands for, it's basically UV coordinates, the vertex texture coordinates.
Ah.
So yeah, so it's basically linking the texture and corresponding vertices. How they're linked, we get there. This one, if you look at the numbers, what does it look like? Like the specification of the examples, the N, what would it most likely stand for?
3D point.
Yeah, that's yay. but those are vector normals, right? So remember last time we need to specify for reflection and like the vector normal which is perpendicular to the surface, right? So facing towards the camera and so on. And those are the vector normals, or different vector normals that are represented. So you find, okay, so that's basically some of the core components that we have. Then the next line here says use MTL, so use material, and that basically says for whatever is coming next, use the material specification called material array PNG, which is specified in the material library, more explicitly. So that's the specification about the material, and this applies for the remainder of that file in this particular case. I forgot, I think it's smoothing. I need to look it up again for what that did. That's not too central anyway. The next one here, however, that's the key that ties everything together. And that's the specification of faces. So that's basically the only thing that links all those different components up where it becomes quite relevant. And what it is, it's basically a one base index reference across vertices, vertex texture coordinates, and vertex normal for each individual vertex that is part of that face, right? So let's try to draw that out. So F basically refers to X. No, hang on. So it's basically V, VT, and VN for X, for Y is V, VT, VN, and for Z the same again. And VN. Just put commas here so we have a clearer differentiation. So, so basically, this face here points to the has the fifth vertex, and it's one base, so it's 1, 2, 3, 4, 5. The first vertex your UV coordinate, and the first normal, this one here, right? So that's the x coordinate for the first phase, basically first, let's say, it's basically modeling triangles, right? So it's modeling triangles here. Second one would be the first coordinate, vertex coordinate, the second texture coordinate, this one here, and the first normal again. This one would be the fourth vertex, the fourth texture coordinate, and again the first normal. And you probably see the challenge, but also the benefit here. You can obviously, the format is compressed in that you don't need to repeat any of the individual metrics, right? You can just reuse normals across different faces. So that's the reason why they have this rather complex index-based format. So the whole specification of the surface or whatever else you see happens here. So that's the face primitive. There's an alternative one, it could be line primitive. That's basically just about, okay, how are vertices connected? You recall the GL primitives, right? GL lines, GL triangles, and so on. That kind of corresponds to those ones in terms of its specification. Faces can don't need to be triangles. They can have an arbitrary number of components, but I think minimum 3. else it's not considered a face but a line. So it's like similar to the triangles and then quads if you want it and so on. That's the idea. Cool. What else? The order doesn't matter. So that's the messy bit. So it could all be inverted, interleaved, or whatever else, which is good and bad, and we get to that in a second. But is that roughly clear what's the structure here about, right? So basically you have the vertices, how eventual textures are mapped if they are found, unlike in my case right now, and the normals of those surfaces, and then how those three are possibly connected. Note, however, you don't necessarily need to have those two ones, right? So vertex normals don't need to be specified. They could also be just inferred based on the available information. But obviously, vertices themselves are kind of mandatory. Please.
But if they are inferred, then the order in which you list them matters for what way the normal is.
Yeah, that's right. So, and the idea is by default, if the system doesn't know, it reads them, the vertices are interpreted counterclockwise. So that would be the order, and that would determine the surface normal. But again, this format is not hard and fast in that respect. So it it depends on your tool. But yeah, in most models they are specified anyway. Yes. So, but there will be a few exceptions we get to in a second. Okay. Since those two are optional, there may be the case, obviously, that you don't necessarily need them.
What was the S4?
No, I need to look it up. Let's look that up, because I put the specification, or I haven't yet, but I will put the specification as far as I found it. I'll show it to you. It looks a bit as old as me, so because I think it probably is. And that basically introduces the whole format. So see if we find it. I will link that specification from our smoothing group. There you go. Okay, cool. Yeah. So what is a smoothing group? That's the idea is there. You can't read that. Sorry. I'm inconsiderate. Must be Friday. It's usually my intolerant day. So. So what's a smoothing group? We get to that. So that's the most common element that we find. And the smoothing group, the idea is there. Everything following an S specification, and right now it was switched off. So all the elements that are following S specification, they would be considered as one smoothing group, and then the surface normal is calculated across all the different vertex specifications that follow the smoothing group component. The idea is there. If you have normals that are attached to vertices, you can have this relatively rugged surfaces, so that you can have a very hard corners in terms of reflection. But ultimately, the normals are used to model reflection, right? So we know it from lighting. So you want to moderate or smoothen the surface, so you don't have hard reflections, and you don't see hard corners in that, Stanford bunny or the like. But actually, you want to smoothen the entire area, and you can do that by using this S specification, and then the normals for all the subsequently listed vertices are interpolated, and only one normal is calculated. So you have a smooth reflection. So that's the idea, right? It basically takes the average of the normals of all the vertices that are members of that smoothing group. Does that kind of make sense? So you have intuitively, you have a rather rugged, kind of rugged surface dish, and instead of taking the individual normals of all that one, you treat this whole thing as a smoothing group, and then even that out across all of them, and then they roughly have a surface normal pointing that direction, right? So then your reflection is much smoother. So if we think about specular effects on the like, as opposed to having really spotty effects here and there, and rugged and hard corners and so on. That's the idea. Yeah?
Does that make something that isn't low poly look very low poly?
I wouldn't go as, it could be, I guess you could, you can have that effect that it looks low poly, but the point is, it doesn't necessarily mean that the lighting will be much more smooth or more softened, I guess, is the impression. But it depends on you how far you go with the specification, right? So perhaps you just want to avoid some weird diffusion effects in this area, or like kind of repeated specular effects or whatever else. So yeah, I mean that's one of the possible results. If you have a too large smoothing group, you may have a very low poly appearance. That's right. That's a good point. But so the idea is basically that you can organize some of the vertices, and that's why this order doesn't matter, but this one does. So we get to that. So just here specification again. We have vertices. X, Y, Z is mandatory UV coordinates, vertex normals. The ones I highlighted here are the ones that are more important in the specification. It's pretty much the stuff you find in any OBJ file. The rest ones is a lot of optional stuff. And if you're terribly keen exploring all the possible options, the specification is your friend. But looking at the elements, so if we model actually geometric primitives, we have points, we have lines, we have faces, that's what we talked about. And here's my take on the regular expression representation of the faces for possible face specification. What I wanted to get at here is that the VT and VN can be optional. So the specification would be along the lines if you, for example, only have vertices, then your vertex specification would be looking like this, right? Combine vertex number 1, number 2, number 3 into one particular face. But you may also have the case that vertex and vertex texture are specified. Then it would be represented like this. And the third case would be that you may have only vertex and vertex normal. So you may actually not have a texture associated with your face. In this particular case, you would write it like this. Now you can check if I got my regular expression right. So those are the possible variants, or of course, by the way, the syntax is actually like this. You have slashes in between to separate them. So that's all possible formats variants. So vertex, vertices, vertex textures, and normals combined. Only vertices, vertex and vertex textures, vertex and vertex normals combined. Okay? Ish? Did anyone find a bug in my regular expression? No? So quite straightforward, right? So cool. That's right. So and this is can arbitrarily be extended, right? Faces can an arbitrary number of elements. Curved surfaces can be modeled as well. Grouping, and that's probably the more relevant one, because right now we had a relatively simple case. If we looked at, that's the one. So here was a relatively simple case, and there's not much fanciness going on. It's probably the most basic OBJ file you can imagine. But you notice that they quickly get quite long. Hang on. Let's use a one that is a bit more involved. Which one do I want to think about? Yep. So let's see. All right, so that is a typical structure of one file. So this one is called Cessna OBJ. So, and I can just show you that that model. Can I? Let's see. Bear with me. Loading is not the strong suit right now. So there you go. And it's basically a model of a Cessna, quite straightforward. But what I actually found a quite good website that gives you a better structural overview. Hang on. and makes actually sense of some of the components a bit more. Let's see. 3D viewer. So that's actually quite nice. Only downside is this thing doesn't allow you to upload material files or textures. It will recognize that you're missing them, but it actually doesn't necessarily ask for them. So you end up with a rather flat rendering. But it has some cool features as that it actually represents what I want to talk to you about, and that's the idea of grouping those faces and making objects out of them. So so for example, here the specification from here to here is a group, right? The idea is there. Okay, so we have on the top, you saw a long endless list of vertex specification and vertex textures and so on. And by grouping, you basically group all the subsequent face specification as one, group that you can manage as in a Blender or the like, or in your any 3D viewer of your points. Particularly useful for slightly more complex models as the one that we may be able to have a look at in a second. Cessna, where is it? No citations. So there you go. Right, there we have our plane. And and it allows you to look at the material specification, which is like, nothing right now, so it's not meaningful. But it recognizes that it misses, for example, the material file that's attached to it. But so you can then, individually deal with the individual groups and identify, okay, kind of debug your model a bit and explore it. So that's the purpose of this whole grouping idea, that you can selectively activate or deactivate features or explore components or remove the flaps, or I don't know, debug your model basically. So that's right. Please. Yep.
So this would also be used to assign different materials, for example, if you want, glass on your windows.
That's right.
Yeah.
Yes, exactly. That's right. That's right. Yes. And looking at the material definition, this sits on a second layer from the grouping, because you may want to, and now we're looking at the bottom, but you may actually have, the same material reused across different groups. So there's a slight dissociation, but it's exactly what you're saying, right? You specify material, and everything following afterwards, which may be grouped, for example, may have that, or will have that material specification until there's a new material specification coming up. Yeah. So that's precisely what it is. So that's how things are fundamentally organized in that context. So yeah, anyway, so those are, and on the next higher level would then be objects, right? So you have an entire plane, right? And you have groups within that plane, but you could specify more than one object in a given file, which probably doesn't really make sense. But if you have more objects in the scene, for example, the Cornell box being an example, then it probably makes sense to spread them out as objects, depending on the complexity. So those are probably the more common ones you find in those specifications. But if you come across things you haven't seen before, look at the specification, I will upload it. But there's also actually a pretty good wiki page on it, but it will mostly cover the basics that we talk about as well. So one of the other things is material. No, this is not a comment, okay. Material, actually, let's talk about material first. Hang on, what is it? Oh yeah, okay, so that's the grouping I just referred to. So again, those are the mechanisms that you can use to organize a particular faces. For example, we have a hood of a car, whatever else, everything following it, all the faces, until the next group is specified belong to a particular group, right? The vertex specification is usually on top, right? So it's a bit like a structured format in that context, because here suddenly order matters. Before that, it doesn't. The important thing, however, is bear in mind it's one-based indices that point to the corresponding components. In this case, this phase specification will only contain vertices, not vertex texture coordinates or vertex normals. Yeah, cool. So similar for objects, just on a higher level of aggregation. Looking at material, we actually come back, and that's why it kind of makes sense to talk about it this week. We have a bit more background now already in terms of what some of the features are. I will obviously not go in full detail because we will have a lecture on material. Currently sourcing a specialist to do that because there's quite a bit of research in exactly that area done at ED. So generally material is maintained in a separate file, specified via MTL lib, so material library, and it's specified in the object type file, and then wherever used, a particular material from that file is referenced using use material, and it's basically just applied to the then subsequent geometry. Actually, so the interesting thing about all those formats, I find there doesn't seem to be a unambiguously authoritative specification. Of course, there's the one that came out of Wavefront, which is, by the way, now incorporated into Maya 3D. But there have been some extensions over time and so on, so there's floating quite a wide range of different specifications on the web. Here's one from 1995, but that should still be reasonably up to date for the material file of how it's supposed to be looking like. So it may remind you a bit of a specification you may have seen from the IETF, from the Internet Engineering Task Force, which is basically just plain text. Man, my system is not responsive, and I kind of know why. Bye-bye. There you go. So, and basically it specifies the characteristics. So here's the roughly the syntax of the material file. Actually, realistically, may not be hacking around with those too much. I think the dealing with the vertices is the more relevant bit. But you basically have a new material definition, you have material color, and then there's follows a lot of statements that are related to the material color, texture information, and reflection information. So it kind of links back to now when we talked last time. How does the material behave in when it's illuminated, right? For example, what's the diffusion effect of that material? Are there specular effects? Is it matte material, or is it is there bright striking reflection and so on? And then also if it has some sort of ambient light effect, which is again a bit artificial, but you have a kind of a base light that is specified in the material as well. In addition to the color and various illumination schemes. I can just bring up the, let's see if we find them. Color illumination. Just bring up the illumination schemes we didn't. So there's, for example, think about them like profiles, where you can have different characteristics of the material. That the material has color, but the ambient lighting is off. That material has color, ambient lighting is on. That there may be highlight focusing on the material, and so on. So that you have glass effects and so on. Refractive effects, so Fresnel, and refraction, transparency. So we'll talk about some of those more, and when we talk about transmission of light through material. But the idea is there that this format specifies like 10 profiles of how illumination can work in a material. So it's obviously somewhat limiting, but it gives you good opportunity to resemble realistic material. That's the key idea there. Specifically for us, more relevant is possibly the reflective element. So we have identified like Ka, which models the ambient reflection characteristics. So either in form of RGB coordinates as we know them. We could have a external file that specified the amount of ambient light depending on some sort of input factors. Or in the CIEY or XYZ, which is kind of a more or less historical color space from the 1930s and so on about the subjective perception of color. And it turns out that we assume steam to be more sensitive to green colors as opposed to blue and red. And the idea that this color space was accommodating that fact by balancing it out. Anyway, so there's various ways of specifying it. So there's alternatives. You can only use one of them if you want to specify ambient reflection for a given material. Similar for diffuse, again using the same mechanism, and for specular reflection as well. NS defines the exponent for specular highlighting. You remember that we talked about the specular component. Obviously, people focus on a particular material, but you can specify the drop off basically in brightness from the given object, right? So if you have a high exponent, then you have a very narrow but very hard, very shiny, very thin reflective area, specular reflection, as opposed to a bit wider, right? If you consider the same range here, basically. And that's kind of, you can specify using this component, so you have a very shiny, sharp material there. Transmission effects, didn't talk about yet, come back to that later. So it would be subsurface scattering, F reflects, or refraction, and so on. And then illumination, I just showed you those 10 profiles that are available. Material textures, as Jona mentioned earlier, mismatch textures that can be provided as well. Procedural textures, so we talked a few weeks ago about the idea of modeling procedurally, landscapes or the like. Can do the same for textures, obviously. So it's basically just some code that is embedded in the material file and run and associated with the face that is currently modeled, and bump mapping. So that gives the idea of varying color to give the perception as if the surface is bumpy, whereas the actual face is actually smooth, right? So we don't have ruggedness effects or the like, or bumping effects on the geometric layer, but only on the material layer. So so when we illuminate how we actually model the surface. Those are the few of those components. A lot of talking from my side. You guys are surprisingly awake. Yep.
Is the bump map does that just alter the color, or does that alter the position of the vertice in the world?
In this context, that's a good question. Let's look it up. I don't think that the material will alter that, but we'll have a look. Bump texture first. So let's have a look. Right, so as far as it goes here, right, so it modifies the surface normals. So yeah, basically just change the lighting effects, right, on the particular texture. So that's it, but it doesn't really change the vertex itself. Just the lighting effects on the particular element. That's right.
You just make it reflect light as if it had a different geometry.
That's right. That's the idea, right? Or less, and then have your dark patches and so on. That's precisely the point. So, yeah. All right, I'll give you a bit of peace for about 8 minutes, I guess. So 11:15 is the round number. You can do it, try and continue there. Yeah, but anyway, cool.